This is a video tutorial for a Polaris calculation. This is a calculation from the HNC CellNav textbook using the 0000 SQA Almanac. So it's the 28th of June and we're told that it is a morning sight. So the sight is taken sometime during morning twilight. The sextant altitude of Polaris, which is obviously a star, is 43 degrees 41 minutes. The height of eye at the time was 8.5 metres. Our position at DR latitude 43 degrees 10 minutes north, DR longitude 037 30 minutes west. The index error on the sextant at the time was 1.5 minutes on the arc. Our chronometer was showing 6 hours 17 minutes and 3 seconds, and the error on the chronometer was known to be 6 minutes and 27 seconds fast. And remember, a chronometer is only a 6-hour clock, so firstly we need to work out whether that is 6 AM or 6 PM for a GMT time. So we've used the Nautical Almanac to find an approximate time of twilight. You can view the video tutorial on that if you want to learn how to calculate that. It doesn't matter whether you take civil or nautical twilight, because you've got a chronometer time, that's giving you the exact time of twilight. You just need a rough idea of when that happened so you can determine whether at GMT it's AM or PM. So on the day, an approximate time of twilight is around 2 hours and 49 minutes. To that I can apply my longitude in time, which is the longitude divided by 15, to get an approximate UTC. So that observation that was given in the question was taken at roughly 05:19 on the 28th of June, so in the morning. Therefore, we now know that that chronometer is saying it is 6 AM rather than 6 PM. I'm going to take the chronometer time and correct it using the error. So if it's fast, I need to subtract that error to get a corrected UTC time of the observation of 6 hours, 10 minutes and 36 seconds. If my approximate UTC had come out as being PM, then I know that that would have been 6 PM and 1800. But it wasn't in this instance. We know that we're in the morning at 6 o'clock in the morning. So using that, the next thing to do, and the easiest thing to do, is turn to the Polaris page in your almanac. You don't have to remember so much with these calculations because the Polaris pages tell you what to do. So if you enter into your almanac, to the Polaris pages, see it says Polaris Polestar tables. At the bottom of that page tells you exactly what to do. So read this in your own book because it'll be clearer in your own textbook. But it says at the bottom, your latitude is equal to the apparent altitude corrected for refraction, which is essentially your true altitude. You can see the video tutorial for that if you need. Minus 1 degree plus the value for AO plus the value for A1 plus the value for A2. So essentially latitude is your true altitude minus 1 degree plus AO plus A1 plus A2. You enter into these tables using your LHA of Aries. So there's one thing we know we need to calculate. LHA of Aries. This determines the column to be used. Each column refers to a range of 10 degrees. AO is taken with mental interpolation from the upper table with the units of LHA. A1 and A2 are taken without interpolation. So we know in order to use these tables, we are going to have to calculate first the LHA of Aries. So using the corrected GMT time that we've calculated, I've found the LHA of Aries. Watch the video tutorial on finding LHA if you need help with that. I've also reduced my sextant altitude down to my true altitude. Again, there's a video tutorial for that. Then at the bottom of that proforma, I've just added in the steps that the Polaris page told me I needed to do. So I had my apparent altitude, corrected for refraction, which is my true altitude, minus 1 degree, plus AO, plus A1, plus A2. So I just need these three values in here before I can find my latitude. I can also use the Polaris tables to find the azimuth of Polaris at the time, and therefore the position line. So my calculation for LHA is being 331 degrees 22.8. So if you look into your Polaris tables, you're looking for 331, 22.8. So along the top we've got the whole 10-degree columns. So 331 lies between 330 degrees and 339. You see down the sides of the tables we've got 0, 1, 2, 3, 4 and so on. So that would be 330. That would be 331. And the next one, 332. So because I'm looking for 331 degrees 22.8, the correction I'm looking for AO, see this is an AO correction, is going to lie somewhere between 0 degrees 35.2 and 0 degrees 34.4. Now to do this we use mental interpolation only, you don't have to use mathematical interpolation. So I'm going to take a value between the two for my 22.8 minutes. And I'm going to pick 0 degrees 34.9 because that lies about midway between the two. So my AO correction first, 0 degrees 34.9 minutes. And that was through mental interpolation. Once I've got AO, I can then find A1 and A2. So they're slightly easier. Make sure you use the same column for these. So I'm still going to use that 330 column. I've finished with the AO corrections, so now I can move down to the A1 corrections. So all A1 corrections are based on our latitude. Our DR latitude in the question was 43 degrees 10 minutes north. So I'm looking in the 40 degree column or section. So 40 degrees in the same row that my AO correction came from. The correction to apply is 0.5. So then next, my plus 0 degrees, 0.5 minutes, taken straight out of the table. Then my A2 correction. Again, use the same column that you took AO from and A1, but now we're looking at A2. So A2 is based on the month of the year, which in the question we were told it was the 28th of June. So using the row for June, the same column from all the other corrections, that gives me a last A2 correction of 0.3 minutes. So finally I'm going to add 0 degrees, 0.3 minutes. Put it all in the calculator. So starting from 43 degrees 33.4 minutes minus 1 degree, then I can add my AO correction, which in this instance was 0 degrees 34.9. Then add the next correction, which was 0 degrees 0.5 minutes. Then add the third and final correction, plus 0 degrees 0.3 minutes, to get a latitude of 43 degrees 9.1 minutes north. We know it's north because Polaris is only visible in the northern hemisphere. So that gives us our latitude. Just to quickly re-go through all of that, we found the correct time for UTC using the chronometer and found LHA. I've reduced my sextant altitude down to the true altitude, as we always do, and then gone into our Polaris tables. My LHA was 331.22.8. So I've mentally interpolated between 331 and 332 to find my AO correction. Using the same column, I've then found my A1 correction for my latitude of 40 degrees. Using the same column again, I found the A2 correction using the month of the year of June, because that's what time it was given in the question. I can then use the same column again right at the bottom to find the azimuth. So at the bottom we've got azimuth tables. So using the same column that you've used up until now, enter in with your latitude. You've got a better idea of your latitude now. We still lie in the 40-degree latitude section. So the correction for 40 degrees, the azimuth for 40 degrees is 000.9 degrees true. Now, because position lines always run at 90 degrees to an azimuth, that means that my position line runs from 090.9 degrees to 270.9 degrees true. So now we've got our latitude that the position line runs through, and that's a Polaris.